Welcome. Now we are going to discuss about thermal problem in Nastran. So for that, I have an example. This is a component which is going to be uh, placed for engine exhaust system. So this will exhaust the temperature from the engine. So this is the manifold assembly. So here I'm taking this component for the analysis of thermal. So I'm going to advanced simulation to start my analysis. So then I'm creating a new FEM file, and here I'm doing idealize. Why? Because I have some small holes in the component, so I need to remove that. So I'm making an idealized part. Before entering, I'm changing this to thermal, the analysis type, so that the environment can come as per the thermal analysis. So now component manifold. Now I'm going to idealize component. So before editing my ideal doing selecting the body and promoting the assembly, sorry, the main fold component. So now I'm going to idealize geometry. So here I'm just idealizing some holes which is coming less than 15 mm dia. So I made it. After that, I want to idealize this face, this face, this, and this, and as well as this, and this. So now I have selected these portions here, here, and here, and here. So I want to apply the idealization. So now the holes are removed, so I can easily go with my FU model. So once your holes are removed, it has to update on the FU model. It is updating now. So now you can see all the holes are removed from my part. So it is an updated message. So now I've got the component updated with the idealization. So now I can create a physical property for 3D mesh. I'm creating a new property. Here I'm assigning aluminum 2024 as a material, and I'm just applying a 3 tetrahedral mesh, and the mesh size I'm defining 8, and mesh collector, make sure you are selected the appropriate mesh collector. So I made the mesh. So my mesh has been created. So now I can proceed for my simulation component by right clicking the FEM part, and I can say new simulation. So here I'm taking a simulation. So since I defined the thermal, here it will come directly to the thermal. So if it not come, just change your analyze type to thermal and change your solution to steady state nonlinear heat transfer. So this is my uh, program. So now I'm going to define my temperatures and programs. So Now I'm defining the convection on the upper surface, and here I cannot select all the surfaces individually. So what I'm doing in the filter, I'm defining tangent faces to select all the upper faces in a single click. So now you can see all the upper faces have been selected in a single click. Now I can define my temperature. The ambient temperature of mine is 250, and the convection coefficient is 100. Now, what I'm doing as my main problem, I have to create here heat transfer through some coordinate system. So then I need a cylindrical coordinate system. So for that, I'm creating a new CSYS by right clicking the CSYS, and you can say new CSYS. Here I'm defining XY origin. XY and axis I'm using the origin, and the point I'm defining XC as 198 and YC as 72.5 and Z as 420. And the x-axis I'm specifying in Z plus vector, and y-axis I'm defining in plus YC axis vector direction. So here the cylindrical output is the coordinate system is a cylindrical coordinate system, and defining the cylindrical coordinate system. So this is the coordinate system which I have defined. So now I can go to define my convection property. See here in the thermal constraint. The thermal constraint which I'm defining is fixed temperature critical. So that means there is a spectral which is going to display the temperature. So here I have to define the inner faces, all the inner faces, so that I'm making the tangent. And if you select any one inner faces, all the inner faces get selected. So next here in the field, I'm defining a formula. This is a formula for uh, temperature constraint. Here in the domain, the independent I'm defining to cylindrical, and the type also I'm choosing the cylindrical. In that I'm defining the coordinate system which I have designed just a few minutes before. So in that formula here I'm placing my formula which I have already created. That means 150 into 1 plus cos, which is unigraphics variance of theta, plus 300 minus ABS of unigraph variance of Z by 1 mm minus 45. This is a formula. This is like a programming language. So I made this formula. So this is the thing I made, and I proceed to OK. So now you can see, once you say OK, you can see the temperature has been created inside. So based on this, I have created the temperature. So I have two constraints right now. So now I can proceed to my solve. Now I say solve. Okay. I'm having problem in my software, so I'm showing you the previous result which I designed. So in that I'm right clicking, specifying the result file. So now this is my result file. So here this is my result. So the temperature is varying from there to here about 599 Kelvin, so degrees Celsius. So this is the way you can do the thermal problems, and you have some other examples also. You can see that, and you will get know how to solve the thermal problem. So this is the animation view. And thank you for this tutorial, and we'll see you again.